Okay, in theory, we're live. Hey everyone, welcome to interview here on my YouTube channel. Today I'm talking with Christopher Morrison, who works with USNC. We will be getting into the name of that company in a second. Chris is I guess the person who wrote the proposal, the person named in the recent NIAC award for an interstellar sample return mission. So today we're going to be talking about what it's going to take to chase down an object like Oumuamua or Borisov. Not only that, orbit, maybe land, and even return a sample. It's kind of mind-bending to think about the possibilities. So, Christopher, thanks so much for taking the time to chat with me today.
Yeah, I'm excited to tell you guys about the projects I'm working on.
Well, first, congratulations on the NIAC grant. Every time a new round of NIAC awards comes out, it's sort of it's like, I don't know, it's like the holidays for me. It's like a birthday present for me, and I sort of look at all the cool proposals and then quickly jump on the call and try and interview as many people as I can because they're all such cool ideas. What was the what was the process for you to actually kind of get this grant?
Yeah, I've proposed several NIACs ever since graduate school. I graduated 3 years ago with my PhD. So even in graduate school, I was submitting some of these and followed a lot of the developments and events. And sometimes it takes a little bit of figuring out exactly what they want. Sometimes it's like, the first one I proposed might not have been the craziest idea. It didn't even get through the screening phase.
Yeah.
There's kind of phase 1A where they say, okay, your idea is cool. And then the phase 1B is where you have to convince them that you're able to execute on that idea and actually ultimately win a NIAC phase 1. So this particular proposal we also submitted last year. It got pretty good feedback, but there were some comments. I addressed the comments this year, and I'm happy to say that I got the blue color. And I think in the NIAC, they have kind of the Roy G. Biv rainbow of, if you're red, you're not very good.
Yeah.
Green is not the like you win. It's the blue. It's the light speed blue kind of, the
right.
shift.
Well, the funny thing is, I think you sort of mentioned it there. It's that balance between feasible and crazy. Like if your idea is too feasible, then they're not super interested in it. If your idea is too crazy, then they're not super interested in it. You've got to strike that balance between an idea that pushes the limits of what is currently done in NASA and space exploration, but also maybe is feasible, can actually get accomplished. So I would love that we can get into this. So let's talk about your proposal. So what's the idea?
So the idea is to actually take an old technology. So NASA uses plutonium-238. They've been using it since the 1960s. And the reason you pick plutonium-238 is it has a very long half-life and a really high power density. And it only emits what are known as alpha particles, which are easy to deal with from a radiation perspective. Sometimes you need a really thick radiation shield for certain types of radiation, but for plutonium, you probably don't want to do it for too long, but you could actually hold one of these in your hand for a very short period of time, assuming it didn't get too hot. But NASA originally looked at a lot of different radioisotopes. They looked at one called polonium-210, strontium-90, cesium-137, and they ultimately decided on plutonium as one of the highest performance isotopes. And they actually looked at one of the ones that I'm looking at in this NIAC. It's called Cobalt-60. It has a very long history. It was used heavily in the medical industry for cancer treatment. They'd get you in a room with some of this Cobalt-60, and they'd have the x-rays that were coming off of Cobalt-60 kind of treat your cancer. And it's a known technology, and the reason NASA rejected it was it has a 5.7-year half-life and it emits X-rays.
Right.
So the half-life is quite short. So fast forward to today, in the past, we've looked at things like going to the gravitational lens, 550 AU and further away, right? That's a distance problem and a speed problem. You don't want the mission to take 100 years, so you have to get up to a high speed. But then when you're there, you actually still have to do stuff. But with these extrasolar objects, it's not a distance problem, it's purely a speed problem. So 5.6 years of a half-life is not an issue here. It's something that, hey, all we need to do is get up to speed fast enough, and then come back before it's too far away. And the innovation isn't so much the technology as a combination of the mission, as well as there's one other key piece, which is regulatory. That in 2019, if I was a commercial company and I wanted to do space nuclear, I didn't have a framework. I didn't have a regulatory framework. I didn't have anything. There's a government framework, which involved very challenging requirements. But in August 2019, there was a National Security Presidential Memo number 20. And that particular memo outlined, hey, if there's launch cases for commercial, and the FAA is the main regulator, or technically the Department of Transportation. And it created a framework where, when we first looked at this, we're looking at lunar landers. We were looking at just couple watt heat sources for lunar landers. And the NIAC is kind of the souped up version of our lunar lander technology. And this basically allowed a commercial case where we could pursue this and launch it and have a regulatory environment that still made sure it was very safe, but would allow it. And kind of the combination of that, and we have some IP associated with this. We have a specialty. When you make these radioisotopes, the big thing you don't want from a safety perspective is release. If any of these radioisotopes get out into the environment, people could breathe them, people could eat them. There's a lot of challenges. And what we have as IP is special encapsulation technology that when we actually make this radioisotope battery, it starts out not radioactive. We take it in a lab, we produce it. We can use, it's actually a very small lab. There's a few pieces of equipment. The complex part is we ship these to a reactor, and the reactor irradiates the actual cab battery, or the cab unit as we call them, and it makes it radioactive. It activates it. And the way we build the ceramic is it's a 2-component ceramic. There's an encapsulation ceramic that is non-nuclear, and there's a precursor ceramic that when it interacts with neutrons and there's other types of radiation, it will turn into the radioisotope we want. And what's cool about this is we can selectively pick. We can say, hey, for this mission to potentially to an extrasolar object, we have the Cobalt 60. But for shorter missions to the moon, we can pick one that, hey, if you're on the moon, you don't necessarily need even 5 years of operation. You might want 1 year.
Right.
So for that particular application, we're looking at a different isotope that has easier X-ray properties. That as I mentioned, the Cobalt puts out a lot of X-rays, but this one is very easy. So to get back to the original question of what is the innovation here? It's a bunch of things. It's regulatory.
Right.
It's the technology that we've developed around easily producing these in a nuclear reactor. But it's also just that these missions to, before this, why would you want to hunt, like the Oumuamua and the Borislav comets really made this very practical use case for this technology.
Well, so I want to sort of first talk about this idea of using like a plutonium isotope as a way of powering a propulsion system. So, when we think about radioisotopic thermoelectric generators, the plutonium-238, it's the one that is inside Curiosity and Perseverance and in the Voyagers and in New Horizons, but it's used, they use a thermocouple to extract to turn the heat into electricity, which can then power the spacecraft for decades. I mean, we're still communicating with the Voyagers, and they're using this system. So how do you plan to use this for a propulsion system?
Yeah, absolutely. It's electric propulsion that we're converting. These radioisotopes don't produce electricity. You have to have some way of turning the heat into electricity. And one of the benefits of these radioisotope systems is, in all reality, they're just dumb hot rocks. They're simply predictable. They're going to produce exactly this much power today, this much power tomorrow, this much power next year. Very predictable. You don't need fancy control systems to control these batteries. And when you use the heat, we can go to very high temperatures. Everything we design is designed to withstand re-entry into Earth's atmosphere from a launch accident. So, we could potentially going to higher temperatures allows us higher efficiency conversion systems. And In space, one of the big issues is your heat rejection. On Earth, we have air and water. And when you want to reject heat for a thermodynamic cycle, it's very easy to reject air and water. But when you're in space, you have only infrared radiation to reject to. And if you don't go to higher temperatures, just like on your stove, when your pan gets really hot, it might turn a little red, right? That means it's emitting a lot of infrared. And this is temperature to the fourth power relationship. So if I'm at room temperature, I emit a certain amount of radiative infrared heat. If I go to 300 degrees C, I have 16 times more heat that T to the fourth. So you're double the temperature, and it's basically 16 times more. So if you look at some of NASA's concept missions, such as the GMO was a nuclear electric propulsion using fission power, a slightly different type of fission.
Yeah.
It almost looks like it's solar powered because they have these big giant radiators everywhere. But in this one, we're using high temperature power conversion, fairly low efficiency because if you get too high of an efficiency, now you're too cold and your radiators are large. So there's this optimization problem where efficiency isn't the big deal here. What is the big deal is power per unit mass. How much electrical power can you get per unit mass? And you feed that into what are now fairly conventional electric propulsion devices. There's a whole bunch to choose
like
from.
Hall effect thrusters and various ion engines and things like that.
Exactly.
Yeah. And so how much electricity? I mean, GMO is, I was reporting on GMO back in the day, the Jupiter Icy Moons orbiter that would have used this, as you say, a fission reactor, ion engines. It would be able to go into orbit around each of Jupiter's icy moons, one after the other. It was a wonderful, monstrous sort of Battlestar Galactica idea of a spacecraft. What kind of well, actually, you know what? Let's talk about about an interstellar object and the kinds of velocities, and then we can use that to sort of figure out what it would take to be able to actually catch up with one. So how much of a challenge would it be? Is it to just even catch one and go into orbit and scan it and send data back? But I mean, the part that made my jaw drop on your proposal was a sample return. So what kinds of velocities you're dealing with here?
Yeah, a little bit about the orbital mechanics. So Oumuamua, we have something called a V infinity, which means the velocity it was going outside of our solar system. When it falls into our solar system, it moves much faster. But the V infinity is a good number to look at because we know the escape velocity to leave the solar system pretty well. And however much excess speed the object has as it was falling into our solar system is kind of what you add to that escape velocity term. And it was moving, I think, about 26 kilometers per second at V infinity, as we call it. When it was in the inner solar system, I think it was about 86 kilometers per second, a lot faster. But Earth also moves around the sun. So Earth is actually moving 30 kilometers per second. So that's why it's not easy a lot of numbers will report, it was moving this fast, but then you have to take into account we're on a moving object around the sun.
Compared to the sun, compared to Neptune, compared to what? Yeah.
So you look at V infinity, you look at how much the escape velocity is from Earth, and then you make some assumptions on how fast you want to catch up to it. Just like if you studied high school physics, you know that acceleration squared times time, or acceleration times time squared over 2 is kind of your position, right? So you can do these really basic high school physics calculations to tell how fast do I want to catch up. And some of it depends on the angle of the object. If the object's coming in the ecliptic plane, which is where all the planets orbit, or if it's out of the ecliptic plane, and you can do some magic where maybe you do a plane change around Jupiter, you do a plane change around the sun, you might be able to get some delta V from the planets. And there's actually something called Project Lyra, where they looked at conventional rockets. And they said, hey, if we had 35 kilometers per second of delta V, we could catch up with Oumuamua in about 15 years.
Yeah, I know that even now, they say that you could put a tiny little probe on top of a Falcon 9, launch it in the next year or so, and still catch Oumuamua if you wanted to, but not return a sample.
Yeah. So to catch up with one, it's on the order of something like 50 kilometers per second at delta V. To go back, it's roughly about the same. You can kill some of that if you fly directly towards Earth and use Earth's atmosphere to slow you down. And one of the things that I mentioned in the proposal is you eject your sample, and your sample is just on a trajectory to intercept Earth and slow down. But there are limits to how much you can slow down using the atmosphere and heating and all that. So really, 100 kilometers per second might not even be enough for everyone. There's some. I did kind of a back of the envelope case, and I said somewhere between 75 and 150 kilometers per second is what you need to do these sample return type missions.
And there is nothing that has ever had that kind of a delta V. Like nothing. Like I think Parker Solar Probe is like the most delta V that's ever been generated for a spacecraft, and it's not a fraction of what you're looking at.
Yeah, it's definitely a challenge. There's a few. There's the solar sail concept that I think it's Explorer and Aerospace Corporation are working on. They got a phase 3 NIAC for that one, and they fly fairly close to the sun. It's not that close to the sun, but they use that boost. You get more effectiveness of your propellant if you're deeper in a gravity well type of thing. Some physics there. So there's some concepts out there where you could use something like a solar sail as in a sun jammer concept. But in the one that I'm talking about, you don't necessarily need to do that. You could fly straight towards the object, or in reality, you'd probably want to do your plane change around Jupiter and then fly straight towards the object. Right. So it's definitely the, from chemical propulsion, no way, no how. Like this is impossible. For electric propulsion, though, what's really cool is you can pick your ISP. If you want to be 6,000 seconds, 12,000 seconds, there's some electric propulsion group out there that will get you that. But the issue is power. That the efficiency of your propellant is mass times velocity. That's a momentum equation, right? The power that it takes, though, is mass times velocity squared over 2. So your velocity energy is a square term, but your velocity efficiency is a linear term. So if you want to get 6,000 seconds instead of maybe 450 in a chemical, well, that's roughly a factor of 12. And now you need 12 to the second power, something like 144 times the amount of energy for that. And that's where energy is such a key piece of this. Is for electric propulsion to work is you need a ridiculous amount of energy. If you can get that, the technology for propulsion is here. We can use these electric propulsion systems. It's just, how do we get that much energy?
So give me an idea then of like how the mission would unfold in your mind. Like, let's say that the LUVOIR has detected an inbound interstellar object. It's on approach. It's on a vector that matches the Earth's direction around the sun. It's close to the ecliptic. You could probably make a flyby of Jupiter if you needed to. What would and you're already in orbit, ready to go. So what would the sort of mission parameters look like?
Absolutely. So what you do is, as you know, they've been studying, I think the Europeans have a telescope that is being designed specifically to look at these extrasolar objects. And I think as one of your articles said that they estimate there's 7 per year into our solar system. So you're relying a little bit on statistics here, that what you would do is you would launch it. And one of the unique things about our launch is we are indeed very concerned about safety. And when we launch it, it would include a very heavy shield, multiple metric tons of a shield. And this is to protect people on Earth. And it's any type of launch accident scenario, the rocket blows up, catches on fire, re-enters the atmosphere type of thing. But once you're in a high enough orbit, you can eject this really heavy shield. You no longer need it. It's purely for safety reasons. And when you eject the shield, you only really need a little bit, what we call a cone angle or a shadow shield, to protect your electronics. Whatever electronics you have a little shield in that direction, and this big giant shield reduces by a factor of maybe 10 in mass. And after you've ejected that shield, you're something like a couple 100 kilogram spacecraft. One of the appeals to this is, you mentioned GMO was this Battlestar Galactica-like thing. When you're at higher power, fission makes sense. When you're at 100 kilowatts, it makes sense. And that's because for a fission system, you need a critical mass. You need you can't have a really small reactor core. It doesn't scale linearly. It's more like once you've achieved a critical mass, you can get whatever power you want out of it until it melts down, or doesn't melt down. But
Right.
Fission reactor is either you can control it. You can turn the power up. You can turn the power down. In these batteries, it's purely a statistical decay process. Produce this much today, this much tomorrow, this much next week, and it slowly decays with something known as a half-life. And once you're when you look at small missions, maybe a couple 100 kilograms, something we could launch relatively quickly on a Falcon Heavy or even a Falcon 9. You want to be in these couple 100 kilograms ranges, because that's, we look at the telecom industry, they put multiple metric ton kind of satellites and geostationary and things like that. So this is what the benefit of this technology gives you, is the ability to get much smaller than than traditional fission kind of electric propulsion, while still attaining the high delta V. What you lose, though, is the ability to control the reaction. So you can't turn it on, you can't
Right.
turn it off, it's always on, it's just producing heat. But it's simple, and simplicity can be very good, but sometimes it can be challenging as well.
And I can definitely sense that the safety issue is an important consideration that you are definitely attempting to address, and that's fine. I think from our perspective, Perseverance launched with an RTG on board, Curiosity launched, New Horizons. There's going to be probably RTGs going on the Artemis mission. That as you say, these are hot rocks that you can encase in protection, and if there's an accident, the thing just lands with a thud somewhere. So don't worry. I get it that safety is a primary issue, and it's fun. Even back during the Cassini launch, we had people just absolutely freaking out about the effect of launching Cassini with the RTG, and so. I'm not concerned about the safety. I'm more interested, not that, let me see. I am comfortable with the safety parameters and feel like that issue has been addressed. And I'm really interested in what is possible with the actual mission. So I just want to kind of go back to our story here. We've got our spacecraft in orbit waiting for a target. It's kicked off its shield, and now it's down to its minimum, its flight weight. What happens next? So
you wait for a target, and you might preemptively fly towards Jupiter, right? What you can do is you're assuming that one's going to come in. You might fly preemptively towards Jupiter, so you can be ready for that plane change maneuver that you're going to have to do to get into the same plane as the extrasolar object. But you kind of camp out, you wait for the one that you want to go after. Then once you find it, the goal is to find it before it's entered the solar system. So the goal is to depending on the object, it might fall in closer or further from the sun. Uma came quite close to the sun. I want to say it was in the inner solar system. Forget the exact path, but it was quite close. And the goal is potentially, if you can get it fast enough, you might not even need to fly towards Jupiter. You can just start speeding up and catch it right in the inner solar system, come grab a sample and fly back to Earth. And that type of mission would only take a couple of years.
Really?
Yeah. It's all about the power source too, that if you can identify this extrasolar object early enough and you know exactly what you want, you can find it at its point of minimum of approach, and this mission could be done in a couple of years. Now, that's getting lucky. You kind of won, maybe not quite the lottery, but you won the bingo round, on that one.
But I'm just kind of imagining that you found your target. It's moving inbound into the solar system. It's in a good trajectory. You essentially shoot your mission outward from the solar system on a track that's going to be able to intercept the object as it's leaving the solar system again. And so you're thrusting, you say, for like a couple of years and sort of picking up velocity, and you're able to match its velocity within a couple of years. I guess that 50 kilometers a second?
Yeah, there's numbers quoted in the NIAC of 5 to 8 I use the number kilogram per kilowatt, or it's called a specific mass. Some people like to invert that number and say how many watts per kilogram, but I like kilograms per kilowatt. And with this technology, it's completely feasible to be in the realm of 5 to 7. And some people will say, hey, like solar is actually, there's a few things out there that are reasonably near term that are up at 10, which is relatively close. But the issue with solar is that's at 1 AU, right? That's, if you have to fly by Jupiter or something like that, you're not going to get that power density. So potentially there could be a solar powered system that if everything was perfectly perfect and this object was falling in towards Mercury, you could look at a solar type system. But with this one, it gives you a lot more flexibility, and especially if you need a plane change, either you do your plane change around the sun or you do your plane change around Jupiter. So it's a bit more flexible. And I think the benefit is just, simplicity on this guy, because it's literally a hot rock, probably connected to a heat pipe with a thermoelectric segments down it and a radiator.
And an ion engine.
There are some complex parts are actually how you do your power modulation and distribution.
Right.
And the electrical components are challenging, and because of the X-rays being produced, you will need rad hard hardware for kind of all those electrical components. You have to worry about shielding, but it's a quite simple system, and that's the benefit of it. Is we could launch this hopefully on a Falcon 9, and part of the NIAC is a large part of it is looking at the power conversion system. A large part of it is looking at the regulatory implications. And a third large part of it is the production. That I talk about these isotopes that we're producing in a reactor. And we know for sure we can get hundreds of watts. The question is, can it be scaled to much higher power? What would that involve?
Right.
With plutonium, they're kind of limited to 1.5 kilograms a year, which is roughly 1.5 kilowatts per year. And the nice thing about these commercial isotopes is that a lot of the issues with plutonium are surrounded around their special nuclear material. And there's a lot of issues with when you say the word plutonium, but if you do these other ones, we think we can drive the price down. So a lot of the work on the NIAC centers around not so much, is this real physics? It's more around, will they let us do it, right?
Right. Well, but I mean, again, the fact that Perseverance, there is now the second nuclear, RTG on the surface of Mars. These regulatory hurdles have been, leapt in the past. So it feels to me like if the prospect here is that you can give scientists a sample of another star system, there are benefits to this. So I just want to go back again. I want to go back to our mission here. You've caught up with your interstellar object, and I guess you're going to go into orbit. The main spacecraft is the orbiter. What would happen next for you to actually acquire a sample?
Yeah, so we would have a payload, and that's something where I'm the, if you think of this as Star Trek Enterprise, I'm Scotty. I'm the engineer telling you, oh, I can take the engines, right? And I would love to talk to some more Spocks, the science officer that can tell me, here's our plans. Here's, the Japanese have done, for example, comet sample returns. The Hayabusa 2, I believe, was a very recent one. So we would probably bring in someone who knows, we will bring in someone who knows a lot more about that. And hopefully, the mass of the payload is a big determinant in kind of our system here, because, if the payload is a metric ton, well, that kind of ruins our lightweight power system, right? So we do need a fairly lightweight sample return.
Yeah, I'm sure it would be grams
to make this work.
Yeah. So whatever, there would be, some combination of, the folks who worked on some of the Hayabusa landers from Germany or from Japan. Like there'd be a lot of people who have a lot of experience in this, or the people who are planning the Phobos sample return missions, etc. They would retrieve a small sample, and then how would the spacecraft would it decelerate, or would it grab the sample and then the whole thing would return back towards the Earth, or would it send a return? Like, would it be like, say, OSIRIS-REx or Hayabusa at this point?
Yeah, exactly. So you're traveling on this extrasolar object, and you're moving rapidly out of the solar system. And your time, how long it takes to get back to Earth, is, again, because these delta V's are so high, you can almost treat it like that basic physics kinematic equation, AT squared over 2. And how far it's moved, how much delta V you have to get back to Earth. The more delta V, the faster you can get back to Earth. And it's going to depend on the extrasolar object. And I've kind of bound it and said, 100 kilometers per second is what we're targeting. There will be some objects that we won't be able to do a sample return on because they'll be moving too fast. They'll be more in the 150 kilometers per second regime. But there's going to be some proportion, and Oumuamua was one of them. If we had seen it early enough and we could have prepared this, we definitely could have intercepted it in this fashion. It was within that regime. And Borislav was also in that regime as well, that we could do it. But there's probably going to be some that are further out and harder to catch. There's even a chance that if someone was really interested in intercepting Oumuamua, we could, instead of doing a sample return, we could do a flyby. We have enough delta V that we could pretty quickly catch up to it and do a flyby. But I think it's too far out of the picture now to do an actual sample return.
Right. Yeah. And so I'm sort of envisioning you're on a trajectory with the interstellar object. You're on your way out of the solar system. You turn in the opposite direction, start to fire the thruster, start to turn that, what is a hyperbolic trajectory into something that's more parabolic, that's actually going to, and then eventually you'll reach the top point of your orbit, and then you'll fall back into the inner solar system. And then the hope is to aim for the Earth at that point.
Yeah. One of the things we'll do is we'll separate out the sample. So a lot of people talk about, if you're flying towards Earth with a very radioactive source, right? The goal would be point the spacecraft a bit away from Earth and eject the sample such that, it's ejected. It might have a small little propulsion system on it as well to kind of bring it into Earth's atmosphere, and then they can go pick it up maybe in the ocean or in the desert, or however, kind of how Hayabusa did it.
So this idea then, I think that tells the whole story of this mission, but the idea of matching an RTG with an ion engine, with a high performance ion engine. That's the most extreme idea for sure. Like something that seemed like complete science fiction, that you could actually chase down one of these objects and bring a sample back home to Earth, just as if it was like OSIRIS-REx or Hayabusa. What are some other missions that you've thought of that would work really well with this kind of just an overall thrust performance, but with a relatively small spacecraft?
Yeah. So the challenge is the time. For this particular one, it's 5.6 years. There's another one we're looking at that's closer to 13-year half-life. So a Voyager mission wouldn't be a good fit here, because Voyager, you want multiple decades. Plutonium's great. Do plutonium on Voyager. Potentially Europa, that if we can get there fast enough, there's a lot of issues with ice. You melt the ice. There's this mission to actually melt through, I think, 10 kilometers of ice down to the ocean. They're looking at plutonium for that, which is still a good choice. But I would say that the Cobalt one might be a bit cheaper. And the whole mission, if you melt through the ice, I think they're only talking about it taking maybe another year or two. So it's still within that realm of feasible with shorter half-life materials. So potentially there could be some cost savings, and you could save that plutonium for other missions where you're looking at longer timescales. So
that's the main advantage of the Cobalt versus the plutonium, is that it's easier to produce.
Yeah,
it just has this shorter half-life.
Yeah, I'll say, plutonium is great, and I'm glad we're producing more of it. And there's definitely things where it still makes all the sense in the world to use that. But I'll say one of the challenges of plutonium is it's very costly. Each RTG is on the order of $1 billion or 400 million. It depends on who you ask. They're a lot of money. It takes time. You can only launch maybe one Curiosity-style mission every 4 to 5 years. at the current production rate of plutonium. So the issue, what I think would be great is, if we can come in with a maybe slightly lower performance, or in some cases it might be equal performance, but just shorter half-life material, and then save that plutonium for the other types of missions where you really need it for that long half-life.
Right. And so like how much of those other ones, like was it Cobalt you said? How much Cobalt 60 is being produced? Like lots?
Yes, so my goal is to get it down a lot, and a lot of that depends on the size of the spacecraft and the scaling of the spacecraft. So for this particular one, we're looking at 20 kilowatts electric is what the proposal talked about. I'm probably going to try to lower that a bit. I might say, okay, if we got it down this low, can we get it to 10? Can we get it to 5? Power conversion is maybe 10% efficient or 15% efficient. So you got to multiply that electric power by a factor of perhaps 10. So, now we're talking about something like 200 kilowatts of thermal power. But the cool thing about Cobalt 60 is it's extremely high power density. So plutonium is 500 watts per kilogram, or what I like to say is half a watt per gram, is kind of in that range. Cobalt 60 can be as high as 17 watts per gram. So it's a factor of 34 times theoretical density. Now, in reality, efficiencies and making things, it never really quite gets to that like high level of extreme, and there's also concerns about cooling, right? You got to be able to cool it. So there's obviously ways to make sure that you get the heat out in a good way. But in terms of just the raw power density at beginning of life, let's not talk about half-lives and how plutonium has a much longer half-life. You can get power densities very much on par with that of plutonium. And there's a secondary isotope that we're looking at, which I can talk more about in the future, but we're probably going to wait a little bit on to reveal that one. That's on par with plutonium, but the benefit of that one is it has a 13-year half-life on that order. So it's a longer half-life, but still not that 87 years you get from plutonium.
Is there anything that's sort of in the other end of the spectrum? I mean, have you thought about if you push this to the very limit, like imagine we wanted to send an interstellar spacecraft, some small probe out to another star system. And like if you took say a plutonium RTG and just let it accelerate for 87 years, or I guess it would be the half-life. So it would probably be continuing to attempt to accelerate for a few hundred years. Do you have any idea? Have you sort of looked into what kinds of I don't know, gulfs could be crossed in reasonable amounts of time because I can just imagine a spacecraft accelerating for 100 years is interesting. Right?
Absolutely. There are a few that are on par with about 1,000-year half-life. The issue is their low power density, so you don't get nearly that watts per gram that you get with something else. But if you're looking at an interstellar mission, or maybe like I forget the von Neumann probe, if you've ever talked about
totally,
those types of things. If you wanted a few watts of power for 1,000 years, that's totally doable.
Really?
Yeah.
So have you done any back of the envelope calculations? Like what would 1,000 years of a few watts pushing an ion engine get you in terms of velocity?
Yeah, the issue is it's just heavier. It's not as good in watts per gram. So where I see it being useful is you have another propulsion source that gets you up to speed, but to power the electronics, or you have to have a camera when you finally do your flyby in 100 years. You got to have something that powers your camera. So I'll say that the performance for electric propulsion, it still could be reasonably good because you're spreading it out. Just to speak orders of magnitude, when you look at nuclear energy, it's roughly 1 million times higher power density than hydrocarbons or batteries. And there's a little bit of variance. Maybe one nuclear isotope is 10 times more than another in terms of the stored energy, a total amount of energy in the isotope. But they're all pretty similar. They're all within that range of 10. So whether you pick plutonium or you pick cobalt or you pick something else, they're all very similar energy densities. But what differs is their power density, because that half-life, the longer the half-life, the lower the power density. So you could potentially get similar delta V's out of a Cobalt 1 as compared to these other ones that I'm mentioning. It would just take a much longer period of time to do those types of operation. And I think, really, I would love, if anyone's listening on the show and is looking at interstellar stuff, I would love to, catch up with you. You can look me up on probably LinkedIn is the easiest way to get a hold of me.
But so have you not done some just back of the envelope calculation to get a sense if this is right now, back in the day, right, the idea was like a Bussard ramjet, but it turns out that there isn't enough hydrogen to scoop in to feed your fusion drive. Ideas for fission drives, but again, you just would run out of fuel. And so the current thinking is it's going to be something like a breakthrough starshot, that you're going to zap a tiny little solar sail with a laser and send it on its way. Does a ion engine matched with an RTG and a patient NASA get you anywhere? Because it seems, I guess to me, it feels very simple. Like that's the part that I'm really enjoying about this idea is as you say, it's a hot rock with a very proven engine bolted on the back, and obviously some heat exchanging engineering problem. You'll sort it out.
So I'll talk. So antimatter is 100% of what you can get out of something, right?
Yeah.
Fusion. There's some reactions that can get you on par with 10% of the mass, right? Fission is closer to 1%, right? But when you get down to radioisotopes, it's usually a little bit less than you can actually get out of fission. Just a little bit, not a lot less. So if you're patient and you can wait thousands of years, sure, you can do your 100, or maybe 500 kilometers per second. You might be able to push the boundaries a little bit. But you won't get quite that light speed, kind of a decent fraction of light. You might be able to get 1% or maybe a couple percent of light speed. The cool thing about the Breakthrough Starship is, gigawatt scale lasers from Earth, that can give you a huge speed boost. And that's what really enables that one. Now, what I would think would be cool is you take these radioisotope battery type systems, and you could then use them to power the electrical power loads, and you might be able to help slow down, or you might be able to control your trajectory. That you put in a little tiny electric propulsion system on there, and your goal is to make sure that as you get closer to the object, you can do a little bit of a course correction, maybe,
right,
to get there. So I wouldn't say this would be, if you want to get there fast, this isn't necessarily the solution for Interstellar, but it's complementary to other solutions. And if you're patient, if you're someone who's like, I'm talking on a time scale of 1,000 years, well, yeah, sure, it'll work.
Perfect.
1,000 time scales.
Yeah. There was a mission called called Project Dragonfly. I don't know if you saw this, not the Titan Dragonfly, but it's called Project Dragonfly, and their idea was to try to send something more significant, like a 1-ton payload to another star system. And so they would accelerate using a laser system, and then they would deploy a mag sail that would interact with the interstellar medium and slow itself back down to an entry velocity as it approached the target star. So, maybe that would be a way to provide electricity for some kind of mag sail that you've deployed to try and slow yourself down. So the laser would accelerate you, and then the RTG would help you slow back down again. But it is kind of a fascinating conversation. So I would love to take some questions from the audience if people are watching now and they've got some questions. Raj Luther asks, so when would the sample return happen? So you talked about a few years, assuming you get like a nice, early detection, how long to rendezvous and how long after that to return?
Yeah, so all of them are kind of, if it was absolute best case scenario, it would be a couple years. If it's, most of the, what would be good is to get a distribution of these objects, after we observe enough of them and say, hey, this is how the average case, this is the worst case, this is the best case. I'll say that, what this particular isotope is looking at is it really needs to happen within 2 half-lives. So the propulsion side of things is, maybe 10 years, 15 years at most. Now, you might be able to cheat a little bit and say, okay, once I'm leaving my extrasolar object, I don't necessarily need a lot of power again because my spacecraft is going to fly off. I just need to push off my payload and make sure that the payload has the intercept with Earth type of thing. So you might cheat a little bit, but all of these missions I'm talking about are definitely 15 years or less.
Right.
In terms of the under propulsion stages.
I guess that is an interesting key, is that the moment you essentially have manufactured the plutonium, the clock starts on your. It's not like you can wait and loiter for the perfect target. You're running out of possible energy, essentially just throwing it out into space until you actually can make the flight. So you have to sort of, it's that balance. You may wait and the spacecraft may run out of power before a good target has been made. But if you do find the ideal target and it is on that right trajectory, maybe you could go the Cobalt route as opposed to the plutonium route if you could do that shorter time frame. That's interesting. Hal McKinney is asking, could an interstellar object be so magnetic that it might pose a danger to your spacecraft? Do you think any kind of magnetism would cause an issue?
It would. There might be some weird environmental effects. I wouldn't think it would. A lot of times, for a magnet to affect you, you have to have a material such as iron or nickel or cobalt, I think, are the three. And I think there's another one, but a lot of times spacecraft are made out of, for example, tungsten. If I put a magnet next to tungsten, just like aluminum, if I put a magnet next to aluminum, a lot of times it doesn't do anything because they're not ferromagnetic. So there might be weird things about objects. A big one could be a debris cloud if you're flying into something that's really messy, or you're, maybe there could be a spin that could be really challenging, that you get there and all of a sudden this thing's spinning fairly quickly, and how do you land on it if it's spinning, and that could really mess up the mission. But magnetics, I think we're generally all right on that.
That's interesting. I mean, we know that Oumuamua was rotating really rapidly and probably would have been impossible to try to dock with. You could stay in orbit and study it, but to actually dock. Do you envision NASA? I mean, I know it's still sort of in the NIAC, just in the NIAC Grant stage. Would you imagine it being like just an orbiter first, and then to go sample return as the second version, as the advanced version of the spacecraft? I think that's how it would probably roll out.
I think so. There's definitely interest in flying by Oumuamua because of how weird the object was, and definitely some speculation on its origins.
Yes,
which I won't comment too much on, but I'll say that there probably is an appetite for a flyby. Because it's so far away, that one would still probably be, the clock is ticking very much on intercepting that one. And you talked about Project Lyra, I think, or you mentioned it. They were talking about if you had 35 kilometers per second at altitude, you could fly by it in 15 years or something to that effect. So that one is definitely on the table, and it might actually simplify the system a lot. Because you might be able to go with a 50 kilometers per second system as opposed to 100 kilometers per second. As you know, the rocket equation is exponentially hard, not linearly hard.
Yeah, the tyranny of the rocket equation. Perhaps a split then. The Project Lyra says we could stick a traditional tiny rocket probe on top of a Falcon Heavy, launch it as quickly as possible, and as you say, get to Oumuamua within 15 years, 20 years, 30 years. Like, the clock is ticking on just how quickly it's getting away from us. But if you could do some kind of hybrid approach, take your 200 kilogram spacecraft, put it on top of the Falcon Heavy, use your Jupiter slingshot, you could cut the flight times down pretty significantly, couldn't you?
Yeah, absolutely. I mean, if we can get, with chemical propulsion, it's all about your mass fraction. And to get 35 kilometers per second of delta V, it's not easy. It's definitely would be, think of like a mini stage rocket. With New Horizons, for example, it had kind of a multi-stage standard rocket, and then it had another kick stage that was a solid rocket propellant. And I think it got a record-breaking, was it 16 kilometers per second or something like that, leaving Earth. I'll have to remember the exact numbers. And of course, I think when it left Earth's sphere of influence, it had like a 16 kilometer per second kick on it, which doesn't necessarily include the ground rocket, because to get into orbit, you have to have that. I'd have to look at the numbers again.
So sorry, which mission was that?
The New Horizons. I think New Horizons holds the record.
Yeah, and they did a flyby of Jupiter as well. I think they had an 11, like the escape velocity from the Earth is, let's see, it's like 42, it's like 18 from Earth. And I think they had 11, I think, leaving Earth, and then got a flyby of Jupiter that kicked them above escape velocity. I forget the exact, don't quote me on that.
Yeah, definitely the planets help you. Like potentially we could still use the planets on this particular project, Jupiter especially. But it would eliminate the weird, in some of the Project Lyra, they're like, we'll do Mars, Venus, Earth, Jupiter, like fly around it's like the grand tour before you finally get slungshot out. And that takes a lot of time. Whereas this, I would say it's probably worth flying around Jupiter, but after that, a straight shot. So it could definitely be some kind of hybrid mission where if you want to get a kickstart, the slowest part of a mission is always the beginning with electric propulsion, because you have so much propellant that your acceleration is low. At the end of the mission, you have used up almost all your propellant. And so your acceleration for the same thrust is much higher. So if you get a kick stage, if you're able to launch on a larger rocket, a standard chemical rocket, or as a third stage, or some kind of vehicle, you could get an instantaneous maybe 6, 7, maybe 10 even kilometers per second of delta V, and that would give you a boost during the most important, slowest time for your electric propulsion. I like to draw out the little charts of, it's like instantaneous acceleration. A lot of people don't like electric propulsion because it's so slow, and that's because it takes time to get up to speed. And with a normal rocket, you can get up to speed instantly. And if you can get up to speed instantly, you travel much further distance in the same amount of time with the same amount of delta V. So a lot of people are like, oh, electric propulsion delta V isn't nearly as good as the delta V of a rocket. So yeah, doing a combined mission where you would do that kick from Earth to get you starting to speed up and then would definitely be beneficial for this type of mission.
Yeah, it's really interesting. I mean, we all think even Oumuamua and Borisov are on their way and gone, and we've lost our chance. But still, I mean, if people were willing to work quickly and put their technologies together, a mission to one of these would be possible. We've got just a couple of minutes left. How does the future play out now with your NIAC grant? So what's sort of your next to-do item? What do you have to do, and what can we expect to see in the future?
Yeah, I'm going to put in a short plug for my company because I need to. So I work for USNC Tech, which is Ultra Safe Nuclear Corporation Technologies, which might sound like a weird name, but we do take safety very seriously. And the parent company is just USNC. USNC is deploying small reactors for the Canadian Arctic. We're working specifically looking at, there's places where they ship diesel shipments up in Canada for multi-billions of dollars. And the Canadian government said, hey, let's get some clean energy up there. So the main company is working on that. And USNC Tech is a nuclear technology company that is looking at more advanced applications. And a lot of them involve space. And with this particular technology, it's called a chargeable atomic battery, or a CAT is what we call them. And what's really cool about it is we started working on this for deployment on a lunar lander, that if you're in a permanently shadowed region, or if you're even just a day-night cycle, your batteries, normal batteries, you have to use most of the power in those batteries to heat the batteries, because the heat is the issue. If your battery gets cold, you no longer have electricity. So our first product, which we're hoping to roll out in the next couple of years type of time frame, is just a few watts of thermal power to help these lunar devices survive. And the NIAC is a sportier version of it that's saying this is using this technology, taking it the next step, but it's not out of reason. And really, the next step with this is we're hoping to do a ground demonstration in the nearest future. And the ground demonstration is very low power. It's not the NIAC high power, much higher power one. But it hopefully will snowball that we have a technology that's not just, the NIAC is the really cool, like, hey, we can do that. And then we have these near-term low-hanging fruits as we build up, eventually looking at more advanced, higher power on the way up to something like the NIAC, actually achieving it. And I think we have a very good technology demo that we can do in the next few years and then build up. You mentioned Project Lyra. I think their time frame is they're looking at a 2027 launch period. And I think I'm completely thinking that if we can prove out the basics and get it up to TRL level 5, TRL level 6, that opens the door to actually maybe flying this in the late 2020s, maybe early 2030s. If we wanted to do an Oumuamua intercept, or not necessarily intercept, but a flyby, or as the Europeans get their resources more online for looking at these interstellar objects and find more of them, just kind of doing the mission where we can prove, hey, statistically one's going to appear here, let's wait for it and launch it. So I'm pretty optimistic about this because we believe in the technology so much that as a company, we're putting our own money into this. The NIAC isn't just this pot of money that's all we have. We're actually developing this on our own. And we see kind of a strong future, not just for this, but also leading up to the higher power kind of human scale fission power systems that you'll need to do kind of lunar and Martian exploration.
Well, people always say, like, why don't we just, I think H7 Apollo in the chat is saying, as long as we agree the best solution for fission power byproduct waste is to jettison into space. So, people always say, why don't we just send our nuclear waste into space? And you're saying, exactly, let's just use it as a propulsion system.
For this particular technology, there's a few nice things about it. One is there's something known as a half-life. So after this amount of time, it'll produce half as much power. So for these batteries, after 10 half-lives, you've decreased by a factor of 1,000. After 20 half-lives, you decrease by a factor of 1,000,000. So for going back to Cobalt was 5.6 years, multiply that by 10. After 50 years, you're 1/1,000. After 100 years, you're 1/1,000,000. Like, this is not doing anything to pollute space, right? It's basically zero radioactivity.
No, for sure. But the point being, you're taking your nuclear as if you're taking nuclear waste, and you are literally firing it off into space, and then using it as
one man's nuclear waste is another man's power source.
Exactly. Yeah.
What this is there's some caveats in that we're not using spent nuclear fuel for this. We're using targets, but yeah, this is exactly what it is. And another little tidbit fact I like to tell people is in every home, you have a smoke detector. And in every smoke detector, you have several microcuries of americium-241, which is a radioisotope. And it's actually one that the Europeans are looking at as an alternative to plutonium right now. So everyone, your smoke detector is actually in your home. And the future is maybe not on Earth, but if you're going to start a Martian colony or a lunar base, whatever, why not have one of these in every home, right?
Yeah.
Have there's already so many other things. If you don't get your balance of, say, nitrogen to oxygen right, you'll die. So what's another possible threat in your home in Mars, right?
Yeah. Well, Christopher, congratulations on the NIAC award and all the technologies that you're working on. I really hope that it does make that shift and climb the technology readiness ladder to the point that NASA does consider bolting this onto some of their future missions. It could, attaching some kind of nuclear system to an ion engine is a wonderful idea, and I think this is a really nice, simple way to approach it. So good luck, and please keep us posted as you develop this into an actual prototype.
Will do.
All right.
Thanks for the interview. Appreciate it.
Thank you so much.
Take care.
Now stop the stream. All right. Thank you, everybody, for watching today. We've got a couple more interviews coming very quickly in the next couple of days. So you're going to see a lot more of this, many more of these NIAC awards. So, all right, stay tuned. All right. Thanks, everyone. We'll see you later.